You ever see those pictures after a big earthquake? One building is just a pile of rubble, but right next door, its neighbor is still standing. You gotta wonder, how does that happen? Well, I'll tell you, it is not luck. It's all about a hidden set of design rules, and that's what we're gonna uncover.
So yeah, that's the big question, right? Why does one make it and the other doesn't? The answer is all about how a building is designed from the very beginning to handle the unbelievable, invisible forces that an earthquake unleashes. And right here you can see what I'm talking about. On the left, you've got a classic, and I mean catastrophic, design flaw called a soft story. See how that ground floor looks kind of empty and weak compared to the floors above it? That's a recipe for disaster. Now compare that to the building on the right. It's uniform, it's stable. Understanding this difference is everything.
So here's the key takeaway. It's not just about making a building strong. You can't just throw more concrete at the problem. It's about making it smart. And that intelligence, that's all in the design choices made way before anyone ever breaks ground. Okay, so where do we start? Well, it all begins with this really fundamental idea that dictates how a building deals with all that seismic energy. It's called the load path.
The easiest way to think about it is like a river. The earthquake's energy is the water, and the building's structure, its columns, its beams, that's the riverbed. The whole goal is to guide that rushing water safely from the very top of the building all the way down and let it spread out harmlessly into the ground.
And this diagram here, it shows you exactly how that river flows. When the ground shakes, the top of the building basically wants to stay put. That's inertia. That creates a massive force that has to go somewhere. So it travels down from the floors, through the walls and columns, and into the foundations. If that path is broken anywhere, you've got a huge problem.
All right, let's get into our first big rule. And this is one you can actually see just by looking at a building from the street. It's all about the overall shape.
Turns out, engineers love things that are predictable, especially during the chaos of an earthquake. Simple and symmetrical shapes, like squares, circles, basic rectangles, they're the best because their behavior is so much easier to analyze. Forces get spread out nice and evenly. This slide shows you exactly why. Over on the left, you see these complex shapes, like an H or a T. All those little inside corners, they act like magnets for stress, concentrating all the earthquake's energy into those weak points. But on the right, you have the good stuff, simple, convex shapes that let those forces flow smoothly.
So what if you absolutely need that L-shaped building? Well, there's a really clever solution. Engineers can actually add what's called a separation joint. It's basically a deliberate gap that breaks the complex building into two simple, separate structures. This lets each piece sway independently during an earthquake so they don't tear each other apart. Pretty smart, right?
All right, on to rule number 2. And this builds directly on that idea of the load path we just talked about. It's all about hunting down and eliminating the weakest link in the chain.
This right here, this is probably one of the single biggest reasons buildings collapse. You know the saying, a chain is only as strong as its weakest link, right? Well, in a building, that weak link is almost always a sudden, dramatic change in stiffness from one floor to the next. This creates that deadly soft story.
And here it is in all its glory. You see this all the time. The ground floor needs to be open for, say, a parking garage or big glass storefronts. To do that, you have to remove a bunch of walls. But now that floor is way weaker, or softer, than all the heavy, stiff floors above it. When the quake hits, all of that energy gets focused right there, and the columns just can't take it. They can buckle, and the whole thing just pancakes. Okay, so we've talked about shape and making sure there are no weak links. But what about the stuff the building's actually made of? That brings us to our third rule, and it's a big one. You have to design a building to bend, not break.
Ductility. This is the magic word. Think of it as the building's built-in shock absorber. It's the ability of the structure to bend and stretch and deform, soaking up the earthquake's energy instead of just shattering. It's the difference between a steel paper clip that you can bend back and forth and a piece of chalk that just snaps in two. Now this gets to the absolute core of earthquake-proof philosophy. Engineers have to make a choice. If something has to fail, what part should it be? Well, think about it. If a column fails, the whole floor above it comes crashing down. It's catastrophic. But if a beam fails, the damage is much more contained. So engineers deliberately design a strong column, weak beam system.
And you can see the result perfectly right here. Look at diagram C on the left. That's a weak column design. The columns have buckled, and the whole thing is collapsing. Now look at diagram B. That's our strong column, weak beam design. The beams are designed to be the failure point. See how they've bent? They've absorbed the energy, but the columns are still standing. the building might be heavily damaged, but it's still up. It's designed to survive. Time for our fourth and final rule. This one's a little more complex, but it deals with a super destructive motion that can rip a building apart. Torsion. We're talking about twisting.
Now, to really get a handle on twisting, we're going to use a really simple analogy that makes this whole thing click into place. It all comes down to a swing set.
So, picture a building as just a big, upside-down swing. The foundation is the sturdy branch it's hanging from, the columns are the ropes, and each floor is like a seat. You push it, and it sways back and forth. Pretty simple, right?
But what happens if you sit way off to one side of the swing? Or what if one of the ropes is much shorter and stiffer than the other? The swing doesn't just go back and forth anymore, does it? It starts twisting like crazy. And that is exactly what happens to a building that's asymmetrical.
This twisting happens when there's a mismatch between the building's center of mass, its center of gravity, and its center of rigidity, which is basically its strongest, stiffest point. When those two centers don't line up, the earthquake forces make the building rotate. This puts a ridiculous amount of stress on the corner columns, and they're often the first things to fail.
So, let's do a quick recap of the 4 secret rules of survival. First, shape is everything. Keep it simple, keep it symmetrical. Second, avoid weak links by making sure you have a continuous load path with no soft stories. Third, design the building to bend, not break, using that strong column, weak beam approach. And finally, don't get twisted. Make sure the building is balanced.
And there you have it. Once you know these rules, you'll never look at a city skyline the same way again. They're not just abstract ideas. They are actual, life-saving decisions that are built into the world around us. So the next time you're walking down the street, take a look around. Now you know the secrets to look for.